Show that a ray will emerge from an air-glass-water interface at the same angle as a ray that emerges from a single air-water interface. Here, if we had a light that was incident in air, and then entered glass with index of 1.50, and then emerged in water with index of 1.33. If we draw in a normal, and we can draw our light ray. Let's pick an angle of 25 degrees. Theta 1 equals 25 degrees. And then we know that the light here will bend toward the normal. We have to draw in a new normal for our new incident point. And then at this interface, the light will bend away from normal. And we can use Snell's law, n times the sine of theta equals n prime times the sine of theta prime. So 1 times the sine of 25 degrees is equal to n2, which is 1.50, times the sine of theta 1 prime. So we find theta 1 prime is equal to 16.36 degrees, and theta 1 prime, which is right here, is going to be equal to theta 2, our next incident angle right here. And now 1.5 times the sine of 16.36 degrees is equal to 1.33 times the sine of theta 2 prime. And we find theta 2 prime equals 18.53 degrees. So our final emergent angle here is 18.53 degrees. And if we had a single air-water interface, here n is 1.0, and 2, or n prime, is 1.33. And this light ray, same incident angle, theta 1 is 25 degrees, and we want to find the emergent angle. So 1 times the sine of 25 is equal to 1.33 times the sine of theta prime. And if we solve for theta prime here, we end up with 18.53 degrees. So this emergent angle is equal to the emergent angle above, because the index of refraction for the incident rays are equal, and the incident angles are equal, and the index of refraction for the emergent rays are equal. So if those three things are equal, that will lead to the emergent angle, refracted angle, also being equal. Even though in the top situation we did have an additional medium that the light traveled through. It didn't affect the final emergent angle because it only depends on the incident and final emergent indices of refraction and angles.